Today we're going to talk about the magnetic force on a current-carrying conductor. The features of this is the magnetic field is like the one around the bar magnet since the ends of the coils are poles. As well, if you increase the current, the magnetic strength of the field increases as well. A bar magnet attracts iron objects to each end of the poles. One end is called the North Pole and the opposite is called the South Pole. If the two bar magnets are put close together, the same poles will repel and the opposite will attract. The direction of the magnetic field at the specific point is the direction that the north end of the compass needle points at its position.
Hard materials include steel, alloys like alchemax and magnetar. They are hard to magnetize, but do not easily lose their magnetism. Soft materials include iron and mu metal. They are easy to magnetize, but their magnetism is only temporary. These metals are often used in the cores of electromagnets because of this. Non-magnetic materials include metals such as brass, copper, zinc, tin, and aluminum, as well as nonmetals. Therefore, all metals are conductors, but not all are magnetic. What is a current-carrying conductor? A magnetic field is produced due to the flow of an electric current through a conductor. A force is exerted by the magnetic field on a magnet which is placed in the surroundings of a conductor. When a current carrying an aluminum rod is placed in a magnetic field, force is exerted on it. The force is reversed when the flow of current is reversed. If the poles are interchanged, the direction of force acting on the current carrying conductor gets reversed. This shows that the direction of the force on the conductor depends upon the direction of the current in the magnetic field. When the direction of the current is at a right angle to the direction of the field, the magnitude of the force is at its highest. The direction of force on the conductor relative to direction of current and applied magnetic field can be described by Fleming's left-hand rule, which will be explained later.
The right-hand rule is used to find the direction of the magnetic field around a wire. The thumb is placed on the wire in the direction of the current. After placing your thumb in the right position, if you then wrap your fingers around the wire, that determines the way the magnetic field points. The left-hand rule is another helpful trick, except using your left hand this time, and it is used to find either the force, magnetic field, or the current. The thumb is used to find the force, the pointer finger is used to find the direction of the magnetic field, and the middle finger is used to find the direction of the current. If the magnetic field is pointing straight ahead, then that's the direction you would point your index finger. Then, you would point your thumb perpendicularly up and your middle finger to the side, also perpendicular to the index finger.
In this experiment, a length of copper wire has been placed in a magnetic field. When a current passes through the wire, there is a magnetic force on the wire. In this case, the force on the wire is upwards. It will be downwards if either the magnetic field or the current were reversed. Whichever way this experiment is done, the wire moves across the field. It is not attracted to either pole. The force can be increased in this experiment if the current is increased, a stronger magnet is used, or if the length of the wire in the field is increased.
Another experiment. The magnetic force on a current in a conductor is also used to make the turning effect in a coil. To do this, the coil needs to be placed in the middle of two magnets of opposite poles pointing towards the coil. With this, the current will flow in one direction on the side of one pole, and then the opposite direction in the other side. One side of the coil will be going up while the other side is being pushed downwards. In this is the magnetic field of both poles that puts a force on each side of the coil, helping it turn. Many motors also use this function.